Hi guys, today we're going to be looking at 3.5 rational functions and their graphs. So take a second, pause your screen and look at the objectives that we'll be covering. All right, so what is a rational function? Basically, to simplify it as much as we can, it's just quotients of polynomials. So you might have two polynomial functions. So let's say that we have one that is p of x and we have one that is q of x. And so it's basically one polynomial on top divided by another polynomial on the bottom. A big thing here is that the domain of the rational function is going to be all real numbers, except for the x values that make the denominator equal 0. So remember, anytime you have a fraction, you have to look at that denominator and find out what values will make it 0, because we cannot have 0 on the bottom. That makes it undefined. So we have to take those out of the equation, so out of the domain. All right, so let's go ahead and take a look at that. So if I am doing the domain of these rational functions, again, it's only the numbers that make a 0 on the bottom, on the denominator, because I don't care if the top equals 0. That doesn't matter to me. I only care if the bottom equals 0. So let's go ahead and look at this one. So if I am going to find out the domain, I don't even look at the top. It does not matter anything to me. I only look at the bottom and I find out what will make it equal 0. How do I do that? Well, I set it equal to 0 and solve for those numbers or number that will make it equal 0. So in this case, I'm going to add the 5 over. And I get that x equals 5. And so I can double check if I plug a 5 in here. Is 5 minus 5 0? Yes, it is. So that would be a number I take out of the domain. So let's look at how we do that. So my domain originally would be all numbers, right? Negative infinity to infinity. However, I have to take this 5 out. So it cannot be negative infinity to infinity. However, I know that negative infinity is smaller than 5. So I'm going to go from all the way from negative infinity until I reach that number I can't have, which is 5. All right, but I can't stop there because it's all the rest of the numbers too. So I use the u. I'm going to union these. And I start at that number I can't have again, and I go all the way to infinity. So that is the domain with all real numbers, just taking this 5 that I'm not allowed to have out. And again, I know it's taken out because I have the parentheses. That means that it is not included in the domain. All right, let's take a look at this one. Again, I don't care what's on top. If I'm finding the domain, I only look at the bottom. So I take that and I say, what are the numbers I need to take out? Well, I'm going to find out by setting equal to 0 and solving for those. Oops. Okay, how do I get rid of the square? Well, I do the reverse or the opposite, which is square root. And in this case, do not forget that anytime you square root, you have to look at the positive version of it and the negative version of it. So I have to take out both plus root 5 and negative root 5. All right, so if I'm writing the domain for this, if I'm writing the domain, I know I'm starting at negative infinity, and I go all the way until I hit my first number I can't have. Well, looking at positive root 5 and negative root 5, I'm going to hit the negative version first, coming from negative infinity. Union, again, it's parentheses because it is not included. I started that number again until I reach the next number. So I've already got the negative root 5. Now I need to take out the positive root 5. So this is going to go from negative root 5 to positive root 5. Again, parentheses, these are not included. They're taken out. And then I can continue on from there, from my positive root 5 I can't have, all the way to infinity. And so it looks kind of long and ugly, but all I did is I went from negative infinity to positive infinity, and I took out the values I am not allowed to have. All right, and let's look at this one. So again, top means nothing to me. I just cannot have that 0 on the bottom. So to find out what numbers those are, I set it equal to 0 and I solve. Again, I get rid of a square by square rooting. So I'd have to look at the positive version of root negative 5 and the negative version of root negative 5. However, what do we know about the square root of a negative number? Well, that would be root 5i, right? And negative root 5i. The I is imaginary. So these are imaginary numbers. So I don't need to take them out. So even though I got two numbers, right, that I cannot have, these are imaginary. That means there is never a number I could ever plug in for x that would end up giving me a 0 on the bottom. And this makes sense because no matter what I square, it will always be positive. And so any positive number plus another positive, that's not going to go to 0. They're not going to cancel out. So that makes sense. These are imaginary. So my domain can be everything because there is no number I can plug in that would give me a 0 on the bottom here. So in this case, the domain is negative infinity all the way to infinity. All right, let's look at what's called arrow notation. So we use arrow notation to describe the behavior of functions. So when we're looking at these polynomial and rational functions, some of them get really weird looking. And so sometimes you want to know, how is the graph behaving? So you really just need to know what these symbols mean. So this right here says as x goes to a from the right. So as it approaches whatever that value a is from the right, this negative does not mean negative. It means as x approaches a from the left. So the plus and the minus are directional. This one is as x approaches infinity. That means as I'm moving to the right of the graph, what's happening. And as x goes to negative infinity, as it moves to the left, what's happening. So let's look at this kind of pictorially. So this would be an example as x goes to some value from the right. So what I would do is I would picture myself coming from the right and looking, where is x going? In this case, as x approaches a, I would say that my y's, or my vertical change, is going up to infinity as it approaches that line from the right side. Again, I'm going from the right to the left because that was the direction it told me to. All right, let's look at this one. So this says, as x approaches this line A, this value A, from the left, that means now I'm going from the left to the right, and I'm looking to see what my graph is doing. Again, from left to right, as I approach that line, it is going up without bounds. So my y's, again, are approaching infinity. All right, let's see this one. So as x approaches A from the right, that plus means from the right. So right to left, what's happening? Now it looks like as I go right to left, I'm going down. My graph is going down to negative infinity. Here's another one showing you as x goes to a from the left. So from the left to the right, I'm looking to see what is happening on my y's. And they again are going to negative infinity. All right, let's look at one with actual numbers. So let's say that I wanted to know as x approaches, I'm going to go -2 from the left. All right, so as x approaches -2 from the left. So here is -2. Okay, so as x approaches -2 from the left, I would go from the left. As it approaches -2, what's happening to my graph? It looks like it is going up without bounds. So I would say that my y, or f of x, is approaching positive infinity. All right, so let's look at, all right, well, what about as x approaches -2 now from the right? What is my f of x doing? So as x approaches -2 from the right. So from the right, you normally think about starting here. However, there's a lot going on this graph. And so -2 is right here. So from the right, it would be here. So as x approaches -2 from the right, it looks like I am actually going down. So as I approach it from the right, I'm going to negative infinity. All right, let's say, what about as x approaches, I want to do infinity. As x approaches infinity from the left. Actually, I don't even need that direction. As x approaches infinity. So infinity is going to be going this way on my x's. So as your x's are approaching infinity, what are your y's doing? It looks like they're leveling out, hitting this horizontal asymptote, and that looks like at 1. So as x approaches infinity, it looks like my f of x, or my y's, are leveling out at the value 1. So what about as x approaches negative infinity? All right, well, if x approaches negative infinity, that means I'm approaching negative infinity. So as I go this way, where am I leveling out at? It looks like my y's are coming down and leveling out again at this asymptote, which is at 1. So that's kind of how you read the arrow notation. All right, let's look at vertical asymptotes and holes. All right, so how do you find out if you have vertical asymptotes and holes? Here are some steps. First, we're going to factor the numerator and the denominator. If the factor on the denominator does not cancel with 1 on the numerator, there is a vertical asymptote at x equals that number. So that means I'm going to have a vertical asymptote. So it's going to be a vertical line. That's why it's x equals at whatever number would equal 0. So if the factor on the denominator does cancel with the 1 on the numerator, then there's a hole at that value. All right, let's take a look at a couple of these. So this says find any vertical asymptotes or holes. Okay, so the first thing I want to do is I'm going to factor both the top and the bottom. So looking at this, the top, there's nothing to factor, it's just x. On the bottom, this looks like I can actually factor using difference of squares. So the square root of x squared is x. The square root of 1 is 1. And with difference of squares, remember I get 1 positive and 1 negative. All right, so if the factors on the bottom, if I can like cancel, right, with the top, then there's a hole. If I cannot cancel, if they don't match, I don't have the same thing top and bottom, then there are vertical asymptotes. So in this case, neither of my factors, not the x plus 1 or the x minus 1, cancel with a regular x, right? So then I'm going to have vertical asymptotes. So where are they at? You have to find out what the factor actually is. So solving, I get x equals negative 1 and x equals positive 1. So these are my vertical asymptotes. So I have one at x equals negative 1 and x equals positive 1. And I went ahead and I attached a picture of what this graph looks like. So you can see that we do indeed have a vertical asymptote at x equals 1 and a vertical asymptote at x equals negative 1. You can see how the graph almost has that invisible barrier where it kind of goes up and just runs right along it, but it does not cross those two vertical asymptotes. All right, so let's go ahead and look at this one. I first need to factor both the top and the bottom. In this case, I don't think there's really anything for me to factor on top. And on the bottom, again, there's nothing for me to factor. So they don't cancel, but I can see if there is anything that would make that be the 0, right? But this looks like I am running into the same thing that we saw earlier, which is an imaginary number. That's imaginary. So if it's imaginary, then I don't really have a vertical asymptote. And here's the picture of it. You can see it doesn't look like there's any space like this one, where I have those lines, right, that where it looks like the graph is pushing up against it, but it's not actually crossing. So in this case, there are no vertical asymptotes. And that's because there's no place that equals 0 on the bottom. All right, let's go ahead and look at this last one. So again, I have to factor the top, I have to factor the bottom. This top doesn't look like it can do anything. On the bottom, I have a GCF. So I'm going to factor out a negative 3x. That leaves me with x plus 3. Okay, so in this case, once I factored that out, you can see how this factor and this factor are the same top and bottom and they can cancel. So what happens is that means that's not a vertical asymptote, that is now a hole. So I do have a hole. At what value? Well, I do the same thing. I set it equal, and I see that I have a hole at x equals negative 3. So that means if I plug this number in, it would be undefined. It would give me that 0 on the bottom, but this really does simplify, so it changes the graph some. So it's not an actual asymptote, it's what's called a hole. But I do have a vertical asymptote because there's another factor on the bottom. It was not just that x plus 3. I also have this negative 3x. So to find out what this is, you set it equal to 0 and solve. And it looks like I have a vertical asymptote at x equals 0. So let's see what this graph looks like. And yep, so you can see how it looks like it's got that vertical asymptote. That graph is, coming and it's like it's hitting that barrier, but not crossing it. So the vertical asymptote looks good. You can see how at negative 3, it doesn't look like anything's going on. If you really, really looked, and a lot of times the graphs like this don't show it, but what a hole really looks like would be just an open space at that value that's undefined. All right, let's talk about horizontal asymptotes. All right, so the line y equals b. Notice it's now y equals, not x equals. And that's because it's a horizontal line now, not a vertical line. And this is a horizontal asymptote. This is what it looks like. So you might have one like this one says, as x goes to infinity, y goes to b, where f of x goes to b, same thing. And you see how it flattens out, right? So that's the horizontal. So this one, as x goes to infinity, y goes to b, which is here as well. So it could come from the bottom, could come from the top. It could also do something goofy like this where it crosses it, but then eventually it flattens out and doesn't cross it. So that happens sometimes with horizontal asymptotes as well. All right, so let's look at the rules for a horizontal asymptote. To find them, you compare the degree of the numerator with the degree of the denominator. So let's remember what a degree is. The degree is always the highest exponent. I know that's a little bit blurry, but we're looking at the highest exponent of the numerator versus the highest exponent of the denominator. And here are our rules. If the numerator is smaller than the denominator, then the horizontal asymptote is the x-axis, or y equals 0. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is y equals a over b, which are their leading coefficients. So you take the leading coefficients and divide them. And if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. There's what's called an oblique asymptote. It's also called a slant asymptote, and we'll look at those in a little bit. All right, so let's find the horizontal asymptote. All right, so this is where we are comparing the degree of the numerator to the degree of the denominator. So the degree of the numerator is 2. The degree of the denominator is 2. So this is where the numerator degree is equal to the denominator degree. So then my horizontal asymptote is going to be equal to y equals a over b. In this case, a is 9, b is 3. It's always the leading coefficients. So I would get y equals 9 divided by 3, which is 3. So I have a horizontal asymptote at y equals 3. Here's the graph of it, and you can see how it has this horizontal asymptote at y equals 3. All right, so let's go ahead and look at this next one. So again, I'm going to compare the degree of the numerator against the degree of the denominator. So if there's nothing here, remember what's there is the 1. So the degree of the numerator is 1, degree of the denominator is 2. So in this case, the numerator is smaller than the denominator. And so your horizontal asymptote is y equals 0. And we can see this is one of those cases where this is my horizontal asymptote. It does look like the graph is crossing it, right? But eventually this is going to, as it goes to infinity and negative infinity, flatten out against that horizontal asymptote. All right, and let's look at this final one. So the degree of the numerator is 2. The degree of the denominator is 3. So this is where the degree of the numerator is smaller than the degree of the denominator. Oh, that's the same. I don't want to do that. I'm going to change this. I want you to see something a little different. So, sorry guys, I think I input the wrong equation, but it's okay. We can fix it. I'm going to change that to a 4. Okay, so now the degree of the numerator is 4. Degree of the denominator is 3. So this is where the numerator is bigger than the denominator, and there is no horizontal asymptote. And if we look at the graph, you can see there is no place where it looks like it's flattening out, no place where it's hitting that barrier for the horizontal asymptote. All right, so let's look at slant asymptotes. So if the degree of the numerator is 1 more than the degree of the denominator, that's when there's a slant asymptote. And this is unless a factor cancels out, because when it cancels out, then like you saw with the whole, with the vertical asymptote, just different things happen. So we're going to find the slant asymptote by dividing the denominator by the numerator using synthetic division. And we like synthetic division, so here we go. So we're going to find the slant asymptote. So this is that case where my numerator degree is greater than my denominator degree. And so there is no horizontal asymptote, but that means that there's going to be a slant asymptote. So to find it, we are going to use synthetic division. All right, so if this is x minus 2, remember that is going to end up being x equals 2. That is our number in our box. And then the numbers to the side are going to be 2, -5, and 7. We drop the 2 down. 2 times 2 is 4. -5 plus 4 is going to be -1. 2 times -1 is -2. 7 minus 2 is going to be 5. This is our remainder. So this is our slant asymptote. We ignore the remainder. Again, I'm going to say that. We ignore the remainder. So my slant asymptote would be y equals 2x minus 1. All right, so let's think about graphing the line. 2x minus 1 means that's going to cross at -1 and have a slope of 2. And so that's where this line, that green dotted line, comes from, and that's a slant asymptote. So where does this blue line come from? Well, that comes from the fact that it has a vertical asymptote at x equals 2. So you can see it's got the vertical asymptote at x equals 2 and the slant asymptote at 2x minus 1, and then that's where your graph comes from. All right, so let's go ahead and practice finding the slant asymptote. So I know I'm going to have one because my degree on the top is bigger than the degree on the bottom. So I can find this by synthetic division. So again, you set your denominator equal to 0. And I get x equals -5. So that's going to be the number in the magic box. The coefficients go beside it. 1, -6, 7. Draw my adding line. I drop the first one down. Whatever is below multiplies to your number in your box. -5 times 1 is -5. I add now, -11, multiply by -5, and that ends up giving me 62. Again, this is my remainder. I'm going to ignore it. So my slant asymptote is going to be x minus 11. So if you were going to draw this, remember this is going to be my y-intercept. So I'd be down here at -11. And it's a positive slope of 1. So up 1 over 1, up, up 1 over 1, up 1 over 1. So I would have a slant asymptote that looks something like this. I actually could, let's go ahead and just sketch this. So I would also, looking at my denominator on my original problem, have a vertical asymptote at x equals -5, because that is what would give me a 0 there. So then at -5, let's just say it's there, I would have the vertical asymptote. So I would end up having a graph that looks something like that. All right, so let's look at actually graphing these. So I know we just sketched it, but let's look at what it looks like to graph it. So the things that I usually find to graph are going to be the horizontal asymptote or the slant asymptote. I also then will factor. So I find those first because I think those are easier to find without them being factored. So I find the horizontal asymptote, I find the slant asymptote, then I factor both the numerator and the denominator, and then I find any vertical asymptotes, my x-intercepts, and my y-intercepts. And then I graph the above and calculate any more points that I really need to know. I know our textbook really likes us to look at the symmetry, because that will kind of help should it be across the x-axis, across the y-axis, across the origin. And so I went ahead, and on the next slide here, I also put those tests for symmetry where you can look at them. So remember, to test for symmetry with respect to the y-axis, you plug in -x for x and see if it's equivalent. If it is, then it's symmetric across the y. So that would be something like this. If you want to see if it's symmetric to the x-axis, then you plug in -y for y and see if it's equivalent. Remember, that's going to be something that's more, oh gosh. I don't even want to try to draw a picture for that, but it's going to be equivalent, or it's going to be symmetric across the x-axis. And then you can look for symmetry in the origin by plugging in -x for x and -y for y and seeing if it gives you an equivalent expression. All right, so here we go. So the first thing that I do, again, is I try to calculate my horizontal asymptote or slant asymptote. And that depends on what it looks like. So in this case, the degree on my top, on my numerator, matches the degree on the denominator. So that is when your m equals your m. And so my asymptote is y equals a over b. And a over b, my a is 3, my b is 1. And 3 over 1 is just 3. So the equation y equals 3 is my horizontal asymptote. So let's go ahead and draw that. So y equals 3 is my horizontal asymptote. So I know that I'm going to have this horizontal line here that creates a barrier on my graph. Okay, the next thing that I do is I go ahead and I factor the top and then I factor the bottom. Looking at this one, I don't think it needs to be factored any. Actually, yes, it does. I see something. So f of x equals 3x minus 3 over x minus 2. The top has a GCF. But even once that's done, there's nothing that is going to cancel out. So now I'm going to go ahead and I'm going to calculate my vertical asymptotes. So for vertical asymptotes, remember it's whatever makes the denominator equal 0. And so my vertical asymptote is going to be x equals 2. All right, so I'm going to come over here. X equals 2 is going to be the vertical line at 2. So I know I'm going to have an asymptote there as well. Okay, now I'm also going to calculate my x-intercepts. So remember, x-intercepts are anywhere that the y equals 0. And what's really nice, I want to show you this. If my y equals 0, anything that's on your denominator, you can just ignore, because the first thing I would do is multiply this over. Oops. Right, I would multiply this over because here it's going to cancel, but you have to do it to both sides, right? So when you multiply over, 0 times anything is still going to be 0. And that happens every single time. So your x-intercepts, this is something really important. It's going to be where you set your numerator equal to 0 and solve. So even though that seems like it'd be a huge pain because you've got these crazy fractions, you don't have to worry about them like they're a fraction. You just have to set your numerator equal to 0 and solve. So in this case, my numerator is 3x minus 3. I set it equal to 0 and I solve. And I just keep solving down. Okay, so my x-intercept is going to be at 1. I only have one of them. So I know I'm crossing here. All right, then I'm going to find my y-intercept. And so my y-intercept is going to be anywhere where my x's are 0. So what I do is I keep my equation and I plug in zeros anywhere I have x's. And then, that's a minus, sorry about that. So 3 times 0 is 0. 0 minus 3 is negative 3. And 0 minus 2 is a negative 2. Negative 3 over negative 2, that's a positive 3 over 2, or 1.5. So I'm going to have a y-intercept at 1.5. All right, so to me, this kind of looks like maybe it's going to do this, right? And I would almost think it's probably going to do this as well. But to test for it, let's go ahead and do our symmetry and see what it looks like. Go with red. Okay, so let's do symmetry. Let me make sure I'm not missing anything. Yep. So you could calculate more points, but let's just check the symmetry on it. So for symmetry, so to check across the y-axis, I would plug in negative x for x and see if it gives me the same expression. That'd be negative x minus 2. Oop. Yes. So it gives me negative 3x minus 3 over negative x minus 2. But this is not the same thing. This is not an equivalent expression to what I had before. So it does not have symmetry across the y. So that means it would not look like this, right? So we're good. To test for symmetry across the x-axis, I would plug in negative y everything else would stay the same, and I see if it's an equivalent expression. Well, if I'm solving, I would divide by -1 or multiply by -1, same thing. And so that would give me -3x plus 3, -x plus 2. That is not an equivalent expression. Those things are not the same. So it does not have symmetry top and bottom. So it doesn't look like this. Okay. So then what about the origin? I'm going to plug in a -y and a -x. Okay. Now I'm going to multiply by the -1. So it's going to flip everything's sign. But that again is not an equivalent expression to what we had. So it doesn't have symmetry about the origin either. But this is going to end up being it. If you wanted to double check, you could test a point maybe here and make sure that it looks like that. All right, so let's go ahead and graph this one. The first thing I'm going to do is I look for the horizontal asymptote or slant asymptote, whatever it has. So in this case, my top does not have a degree. So the top, my degree is 0, and the bottom is 2. So in this case, the top is definitely smaller than the degree on the numerator or denominator, sorry. And so my asymptote is at y=0. So over on my graph, I'm going to go ahead and graph the line y=0. That's going to be my horizontal asymptote. Second thing I'm going to do is I'm going to factor the top and the bottom. So if this is my equation, the top, there's nothing I can do. It's just a -4. The bottom does have a GCF. So it's factored. There's nothing to cross out on the top. So I don't need to worry about that. However, I can find my vertical asymptotes by setting both my factors on the top equal to 0. So there's my first one, x=0. My second one is going to end up being x=3. So I have two vertical asymptotes, one at x=0. So here's a vertical asymptote. And then one at x=3. Okay, so then I'm going to go ahead and I'm going to calculate my x-intercepts. Remember, for this, I just have to set my numerator equal to 0. But in this case, there's no x. It's just -4=0. That is not a true statement. So there are no x-intercepts. So I know that however I draw this graph, I can never cross the x-axis. All right. Then let's go ahead and calculate the y-intercepts. All right, so my y-intercepts, I'm going to set my y equal to 0. Or sorry, my x equal to 0. Y equals 0 squared minus 3 times 0. And this doesn't make sense either because I get a 0 on the bottom. That's undefined. We can't have that. So there are no y-intercepts either. Okay, so what's this going to look like? We might have to actually graph some other points to see what this looks like. So at that point, I would say, all right, let's go ahead and test one. Let's test at -1. Let's see what it looks like. Let me erase that. So -1 squared is 1, and that's going to be +3. So I get 4/4, which is 1. Okay, so at -1, I'm at 1. All right, so this looks like this. I know that I have to somehow connect this where I don't touch the y and I don't touch the x. So I'm going to say this is probably going to look like this and go along there. Okay, what if I want to plot one? Let's try at 1. That's a nice point in there. So f of 1 is 4/1 squared minus 3 times 1. So 1 squared is 1 minus 3. So 4/-2. So that looks like that is at -2. So at 1, I'm at -2. All right, so I know I cannot cross the x. I cannot cross the y. I cannot cross any of those vertical asymptotes. So I would guess that this looks something like this in the middle. And we could test another one and see what it actually does. I probably, if you're really doing this, I would test some more points in there. And I'm going to go ahead and do one over here at 4 as well. So f of 4 is going to be 4 squared minus 3 times 4. That's 16 minus 12. So 16 minus 12 is 4. So I'm at 1 again. Okay, so at 4, I'm at 1. Again, I cannot cross the asymptote. I cannot cross the horizontal asymptote. So it is probably going to look something like this. And there we go. All right, guys, I'm going to go ahead and skip over that other one. And let's look at writing an equation. So I want to write an equation that has an x-intercept at 3 and vertical asymptotes at 4 and -1. Okay, so let's think about this. An x-intercept at 3. X-intercepts, we know, are when we put the top equal to 0, right? So x-intercepts are on the top, and vertical asymptotes are when the bottom, you set that equal to 0. All right, so I know that the top would, when I set it equal to 0, is going to have to equal 3. So I would say there's my top. If I set that equal to 0, it's going to equal 3. My vertical asymptotes are on the bottom. So remember, when you write them in the factored form, the sign always flips. So if I need one at 4 and -1, it's going to look like -4 and +1. That's why this +3 looks like a -3. So there is my equation. All right, let's do another one. So f of x, and it has x-intercepts at 0 and -2. So 0 and -2, and a vertical asymptotes at -5 and at 7. Solving it down, it would be x minus 0 is just x. And that would be +2. The two negatives make a positive. On the bottom, it'd be +5, again with the double negatives, and x minus 7. And there we go. There's our equation for a graph that had that. All right, guys, I hope that you have learned something today, and I will see you next time.